So coming up next, we have our next speaker. I think we have two speakers now. I'm gonna add them quickly to the platform. Hi, Sybil. We have Sybil Fisher from EOS.
Hi, Swati.
And Vanessa Seidensworj from EOS as well. Hi, Sybil. How are you doing?
Hi, Swati. I'm fine. Good to be here.
Wow. Thank you so much for joining in. Hi, Vanessa. How are you doing?
Hey, thanks, I'm good. Great to be here.
Thank you for so much for joining us today. And let me welcome both of you to our platform and TIPE 2023, and that too in the supply chain and sustainability track. We have Sybil over here, Sybil Fisher and she is a material developer, polymers from EOS. And we have Vanessa Seidensworz. She is a product manager, polymer materials from EOS. And today they'll be talking about sustainable manufacturing with polymer laser sintering. So I would request one of you to start sharing your screen so that I can make sure your presentation is visible to all of us. And then floor is all yours. Perfect.
Perfect. Perfect. Thank you,
Yes,
Swati, for the introduction.
Yeah. Thank you so much. And please go ahead with the presentation. Have a lovely time.
Perfect. Thank you. Welcome from our side as well. Swati already gave a quick introduction, but it's a bit that everybody knows who's talking today. Sybil?
Sorry, my presentation is not moving on yet for me.
Okay. Sorry.
Okay. Here we
now
go.
It's working, right? Just to avoid confusion. Can you hear me, guys?
I can hear you, Vanessa.
Okay, perfect. Good. Yeah. Good. Sybil, do you want to say 2 more words about yourself? Because Swati already gave a quick introduction, but maybe you want to add 2 or 3 things.
Just very briefly. So my name is Sibylle. As you can see, I've been with EOS for more than 8 years as a material developer since the beginning, and I'm a trained chemist and physicist.
Perfect. Thank you, Sibylle. Sibylle will go a bit into the technical details later, so it's good to have a chemical expert here with me. So my name is Vanessa. I'm a mechanical engineer originally, and I started at EOS 5 years ago as a technical sales engineer, now into product management. And I'm happy to have Sibylle with me to talk a bit about the sustainability aspect of our processes in the polymer additive manufacturing world. So what are we talking about today? Let's have we give a very, very quick overview about our company, a quick introduction into laser sintering, but then jump directly into the topic of sustainability, which is our main topic today. So let's have a quick overview. So EOS, it was founded in 1989 by our company founder, Hans Langer. It's still a private company. Now our CEO is Marie Langer, his daughter. We have currently 1,400 employees worldwide, an installed base of 4,400 systems. Approximately, we are active in metal and polymer systems business. So a very broad additive portfolio, let's say. Besides the technical facts and figures, EOS also established a company purpose 3 years ago, which is responsible manufacturing. Our CEO, Marie Langer, later this day will also in this track go a bit more into the details, but just to give you a rough overview what that means. For us, this means to act sustainable and look at two things of additive manufacturing. On the one hand, what are you producing? Aspect, and then in the end, how he produces the whole value chain behind it. on the one hand, very technically looking at all aspects. That's what Sibylle and myself will be talking about. But there are also, of course, social aspects in how you set up your value chain in the end. But more on the whole purpose of EOS, as said later by Marie. Otherwise, let's just quickly dive into laser sintering in general. You know all the basics is additive manufacturing. We have the digital model. We slice it into layers, and then we fuse the layers together. In our case, we are working with powder. So it's a powder-based process. In this case, a plastics powder, and we melt the material with a laser in the end to get the final part. The general advantages, you might already see here that this might go in a very sustainable direction. So the main aspect you all know is the freedom of design we can achieve with additive. So you have lighter parts, you can integrate functions to build more complex parts that are more driven by the end use that you need to achieve. You can easily customize parts and produce that. And then of course, save material that might otherwise get lost in other production methods. But in details, is it really that sustainable, and what are the different aspects of sustainable in our 3D printing business? Let's quickly dive into the main topic for today, sustainability. What is the status quo, and what are the levers that we can tackle in the future? Because we are not yet there. There's always potential to improve. So let's have a look at the different steps. In general, the status quo, if you look at the global warming potential of the laser-powered powder bed fusion process, you see there are two main drivers that define the ecological footprint of 3D printing. It's electricity. You see on the right-hand side, compressed air plus electricity. Those are both created by electricity. That's 1/3 of the footprint that we leave. And then a huge footprint is the material and its convective refresh rate. That means 2/3 of the global warming potential of a part are defined by the powder itself. And maybe to give a bit more context, what we will be talking about as well is the refresh rate. The powder ages in the system, so the heating process that affects the material ages the powder. So to get a stable quality, you will have to add new powder to the process to have a stable part quality in the end. Just to give you a bit of a background, because we will be talking about the refresh rate in the later slides. Let's have a look at the process chain and the influencing factors. We have on the one hand the part design. Then we can look at the material. We put it all in the printer. That's where the process happens. And then in the end, we need to unpack the part and post-process to get the final results or the final properties of the part. And in each and every of those steps, you will have factors that influence the sustainability of the whole application. So let's start with the part design. The part design and selection has a huge influence about how sustainable the application will be. So on the one hand, if you have a small lot size per part, it makes absolutely sense to go for additive. If you have a huge number, millions of parts, it might make sense to go to the traditional injection molding tools, because this is a highly efficient production process that has been improved for 10, 20, 30, 50, 100 years. Whereas AM is quite a young technology compared to that, but in AM you can do small lot sizes where needed. On the other hand, lightweight design, saving materials, creating more complex parts which are not feasible with other technologies, that's always an option to go for AM. And then, of course, talking about complexity, once you integrate more functions into one part and increase in that way lightweight functionality and complexity, that's also always an ideal part to think about additive to produce parts in one step instead of needing several assembly steps, transport in between, producing different parts, assembling them together. That's all aspects that go into the evaluation of sustainability of a part. So in general, thoughtful choice of parts and the design for an AMM enables really sustainable manufacturing in the end, at the beginning of a process chain already. And to give you an excellent example selection, we brought you a use case from a customer of ours, which is Umabo. They are printing eyewear. In this case, you see already they are doing customized eyewear, so going really into the small lot sizes and getting the potential of the application out of there. They also have a dedicated AM production company to improve all the processes around it, and they have a local production made in Germany, in this case, to deliver to the German or European market from Europe. Looking now at the carbon footprint, you see on the left-hand side, compared to a conventional eyewear, which is the green column here, it makes sense because the carbon footprint is like 44 to 58% lower compared to the traditional manufacturing. So here, having found the right application to use additive manufacturing, it has an impact on the sustainability of the application. It shows the application is more sustainable in this process than in another one. But looking then in the middle of the slide, the pie chart, you see what has the highest influence of the carbon footprint. And there you see again the bright green. That's the polyamide that goes into the raw material, which has a huge influence. And in that step, I would like to hand over to Sibylle to give you a bit more information about what is the potential to reduce that huge part of polyamide influence in that application.
So thank you, Vanessa, for this first part. Speaking of the material, we have seen now several times that the material has the biggest influence on the carbon footprint. We have two ways to gain the raw material for the base polymer. The one is the classical fossil-based plastics, and other ones are bio-based or plant-based mainly. So the share of bioplastics in the whole industry currently is just around 1%. In additive manufacturing, at least in laser sintering, we're speaking about 5 to 10%, which is mainly driven by the use of PA11, which is based on castor beans. But also making the base polymer have to make a polymerization. Vanessa, could you go? Thanks. Make the polymerization and really generate the plastics. And we have levers to increase sustainability here by, for example, using renewable energy or improving the production efficiency. Now we're having our base polymer, and we have to make that base polymer into a powder and sometimes even modifying it, for example, by compounding additives or fillers. For the powder production, the same accounts then for the base polymer production. I can improve my production efficiency. I can use renewable energy, but also increase my production quality in order to have lower scrap rates. And I have the potential to incorporate recycled materials. So there are quite a few levers in order to have a more sustainable material, but you have to have the right one. Going to the next slide, we now have our polymer powder, and it's now processed on the laser sintering system. And there are several different things that actually influence the power consumption of the system. That's the temperature on the one side, because as you might know, it's a hot process, and we're processing the plastic powder at a temperature a little below the melting point. Which temperature we're using to produce the part determines the part quality, and of course it needs a majority of the energy. Then on the other hand, we have the processing parameters. They determine the layer time, they influence part quality of course as well, and processing parameters are part of our core know-how. We talked about the refresh rate. The refresh rate is a huge lever for the global warming potential because it determines how much leftover powder we're having, even if it's none at all. It's very dependent on the material. The more a material ages and changes during that hot process, the lower the refresh rate is, meaning the more new material I have to add in order to have a stable process. This refresh rate can be influenced, for example, by the stabilization of a polymer. So I can really chemically stabilize a material, but that's hard to balance. And it's, as I said, dependent on the polymer aging and degradation. And lastly, I've got the time. The longer my process runs, the more energy I need, especially for heating. So this is a result from the processing parameters and the material requirements. Summarizing this, the temperature, the processing parameters, and the refresh rate, they all have an influence on the part properties, meaning mechanical properties as well as surface properties. So how much details I have and how clean and even my surface is. Looking at the processing parameters, they're dependent on the temperature, on the refresh rate, and on the time. So depending how the temperature is set, I have to add more laser energy or less laser energy. Depending on what refresh rate I'm running, I have to adapt my process in order to work with aged powders. But then again, the temperature and the refresh rate, they influence each other as well. Because if I'm able to process my polymer powder at a lower temperature, I can, for example, use a different refresh rate because I'm aging my powder less. So if you look at these and all these nasty arrows here, you can see that there are a lot of things influencing each other. And that's why it's quite tricky to actually balance all of these parameters to get the best out of the best part properties at the lowest possible global warming potential or carbon footprint. And that's why this is really core know-how of our material and process development departments. Okay, now we have processed everything on the machine and we have a part actually. Could you go to the next slide, please? I'm taking the parts out of my powder bed now, and what I have to do in addition is dedusting them, get rid of all the residual powder. The problem is this powder is sticking in cavities and it's sticking to the parts. And even if I try to clean them as much as possible before blasting them, our powder loss is surprisingly high. We have a powder loss of up to 10% of the original used powder because of all these tiny cavities where there's still powder sticking. And I have two problems with that. It's actually hard to get it out. And if I have blasted the parts and I have this residual powder blasted off, it's contaminated with the blasting medium. So even if I would like to reuse this waste powder, I have to separate it from the blasting medium. So this powder removal is quite a lever to even reduce the powder usage more, but we have to see how we can reduce the powder that's blasted off. Okay, looking what our status quo is. Where are we now? At the moment, US is offering a carbon-reduced PA12 and a climate-neutral PA11. How is that done? It's mainly done by using renewable energy for the polymer and the powder production process, while we still have a little bit of CO2 footprint left, which is then, in the case of PA11, offset by acquiring certificates. On the other hand, we still have leftover non-reusable powder. We're not at a zero waste process for most polymers yet, but we offer solutions to have a second life for the non-reusable powders. We have companies that actually make this powder, this residual powder, into new pellets or filaments for other fabrication methods. And in the end, we talked a lot about the whole process chain and how important it is to actually use the right parts and set up an efficient process chain. And for that, our Additive Minds consulting section is offering extensive consulting. This is something EOS is offering, but I guess it accounts for probably most of the companies. We're not that different. So, but what's coming up? What's next? I mean, I'm a material developer, and I can assure you we're constantly working on new materials, especially on improved materials for lower refresh rate. For the best case, to not have any residual powder left at all. But it's not that easy, else it would be faster there. On the same side, we have our process development department who are working on new processes to work with even older powder and still get good parts with good surfaces and mechanical properties out. Every new machine generation has improved systems, operates faster in the best case. Faster means using less time, that we have a heating running, a laser running, and they working more efficient. We keep still working on recycling strategies for waste powder and scrap parts. And also we're thinking of some strategies to actually reuse contaminated waste powder. And in the end, there are still projects going on about automated unpacking and dedusting systems, which ideally would help to reduce the waste powder in the blasting process. Now, speaking of recycling, why can't we not just use usual, collected plastics? Well, the requirements for laser powder bed fusion powders are quite high. We need a semi-crystalline material which has a certain sintering window, meaning a temperature range between the crystallization point and the melting point in order to efficiently process it. We need the right kind of stabilization. So we want the powder, or we want the polymers to change a little because it benefits the mechanical properties, but we don't want it to change too much and to age too much. We need the certain viscosity, because if it's too liquid, it will just flow away. If it's too viscous, the particles won't go together, won't melt together. And we need the right grain size distribution. So using just collected plastics will probably not really happen. It's hard to accomplish with classical recycled materials. In addition, the polymers that are usually used for packaging and bottles, these are not the polymers usually used in powder bed fusion. So we have to think of other things. But we have some projects running, or actually one specific project, which is about the recycling of laser sintered scrap parts. This is a PhD thesis of our colleague Karl Freihardt, working at US. And he's trying to make not just scrap parts, but also demo parts and prototypes. And of course, this huge amount of test specimens we're printing, he tries to make that back into a laser sinterable powder and regenerate the powder. On the other hand, there are companies that are offering regeneration of degraded material. There are different methods available. There are also different patents, but there's one drawback. That's mainly offered for polyamide, because of course polyamide has the biggest share in the market, but there are still other polymers as well. So that was our talk for today. I would like to thank Vanessa for giving it together with me. I want to thank you for being here and listening, and we're open to questions now.
Hope our participants had a lovely time hearing you. We do have a couple of questions, and all of you, all the participants, feel free to drop in your questions in the Q&A section for us. In the meantime, I'm gonna go ahead and ask, Sybil and Vanisha, a question which is kind of, I mean, out of my personal curiosity. I mean, when you talk about mixing powders, and the ratio of mixing powder has an impact on mechanical property, object which do you guys manage? I mean, what's the ratio of your powder mixing?
So currently the recommendation is to mix the powder 50-50, which means 50% aged powder and 50% new powder. And as you can imagine, from the 100% of powder that has been put into the job in the beginning, we convert about 10 to 15% into parts, or maybe 20%, but then there's still 30% left. And then, of course, the waste powder that's left over while dedusting. And we definitely have to improve this ratio. And we can improve this ratio by either modifying the material for a better refresh rate, means less aging, or we can improve it by improving the processes in order to work with aged powder and still getting the same or nearly the same mechanical properties.
Mm-hmm.
And maybe to add on that, Swati, I mean, we're not talking a lot about polyamides because it's one of the main materials, like in laser sintering. But if you look at other materials like TPU, for example, there we are already really, really low with refresh rates. So when we do our development process in-house, we usually have the problem that we have to scrap enough powder out of the old job to get enough for the new one. So in certain materials, we are already very, very at the optimum level, basically, with TPUs, for example, but there are other parts where we are not yet there, and that's the road ahead, basically.
I mean, I would love to know what are the basic, challenges when you are recycling your powder. Or have you started doing it yet, or is it under the process, under the project? So I would like to know more about it.
What do you mean
Yeah.
with recycling the powder? Because
Yes. So I heard that you still working into the recycling strategies, right? So those strategies has, how far it has gone, or what are the strategies which you are planning to adopt in future, so that there are less wastage in future.
Mhm. So they say there are always different ways of how you think about recycling. On the one hand, of course, you want to use the material back into your process. That's the ideal process. And then there are also options to use it for different processes. We are working with a partner that collects basically our powder and transforms it into granules for injection molding, for example. So we are already working with partners to develop this second life, let's say, for the used powder already. So if there's customers needing that, we're here to support already. And then, of course, you have
That's
like, what are you doing with scrap parts? Those can be also handed over to our partners to do granules out of it or filaments, whatever is required from the market to use the powder or the parts for.
And when you talk about the ratio, how the mechanical properties, I mean, when you do polymer laser sintering, how does it impact the whole overall mechanical property or surface property of the when you use the reused, what percentage of the reused powder to kind of maintain the mechanical properties intact, or the desired microstructure, the grain microstructure for that matter?
Mm.
at the moment, this is dependent on the material. For the polyamide 12, this is the 50% we've just mentioned. And
Yes.
the mechanical properties we're communicating, they're optimized to this refresh rate. So considering that the customer is running a closed cycle with always the same refresh rate,
Mm-hmm.
it's lower for other polymers, and it's partly higher for some specialty materials. And
I
what we're
mean,
doing at the moment is actually trying to ease or make this refresh rate better, to have no waste powder left at all.
so there must be a lot of trial and error and experimental goes when you are kind of experimenting with the mixture, powder mixture, when you have to kind of attain a particular mechanical, say like you want to have a tensile strength of 100 MPa. So is there any certain standards which we should follow, or EOS follows when it comes to maintain suppose a polymer PA12, and I want the of the material, the printed part, to be 100 MPa. So in that case, is there any standard which you guys?
The standard would be either using the recommended refresh rate, We offer for customers that would really like to do a deep dive to measure the viscosity of the aged powder and adapt the refresh rate according to the measured viscosity. But that means really a bit more of a commitment. That means they have to have the right measurement devices and dive deeper into the topic. But with the
Lovely.
recommended refresh rate, you normally should be able to get out the properties that we're advertising.
Yes, I understand the whole process, and it's very difficult to, kind of, if you have a standard in place, then you can kind of navigate through the process and have the desired properties. With that, I would like to thank Sybil and Vanessa for for being here for us today and sharing the insights. The kind of work which you guys are doing is kind of